This video is about regression performance and linear regression. The performance operator and its variants allow the results of a classification or regression process to be calculated. Given no numeric labels, the performance of a model using numeric attributes to predict this label can be calculated, and this modeling is known as regression. So what we'll cover is linear regression, the actual operator. We'll give a commentary as we go on the regression process and what it means. We'll look at the main features of the performance regression operator, which means we'll need to understand the performance vector. There's a nice operator called performance to data that changes the performance vectors into example sets. We'll use that because it's quite convenient. And then we'll also assess what happens as you change the number of examples and as you change the ranges of attributes by normalizing. So as usual, we have an example set. So this example set makes some data. Doesn't matter about the details. Some training data goes to the top and some test data goes to the bottom. I have set some macros up here. These work inside this sub-process to change the shape of the data. So as we go through, we'll change these macros to make subtle changes to the data. We can change the number of examples, we can normalize it, and we can make it noisy, less noisy or more noisy. The linear regression operator here simply makes a model which is passed to apply model, where the test data is used with the model to make some labeled data, which is passed to the performance regression operator here, where a performance vector is output to performance to data, the operator I mentioned earlier, where we get an example set here. So if I run the process all the way through, we see here's the training data. It's got a result, which is a label, and 5 attributes, and they're all numbers. And you can see that the numbers each seem to be in a range 0 to 1, with an average about 0.5 and a deviation of 0.2, 0.28. And you could spend time looking at that. Let's have a quick look at the 3D scatter plot. Doesn't show it brilliantly well. What I'm doing is I'm colouring the point in based on the result, which is the label, and I'm plotting at 1, at 2, at 3. I happen to know that at 1, at 2, at 3 do drive the value of result, and I guess you can, if you sort of squint at this, you can see that as points are closer to the origin, they're bluer. As they're further away, they're redder. So bottom left here blue, top right here red, sort of, and that's a hint to the function I'm using to generate the data in the first place. And the linear regression operator, its job is to find that relation. Going back to the data, so we have 900 examples for the training data, and we have 100 examples for the test data. So this test data is the result of the model that's been applied, but we're jumping ahead a bit. Let's look at the output of the linear regression first. So what you're seeing here is, if I click on the description tab here, this is what the linear regression model thinks is how the result is calculated. So it's 0.11 times attribute 1, 0.18 times 2, 0.31 times that 3, plus a constant. And what you can do is you can look at this table here to work out how relevant and how good these coefficients are. Basically what you do is you look at the coefficient. This is an estimate of the error. This, the t-stat, is how many standard deviations this coefficient is away from 0, and this p-value is a probability that the coefficient is 0. In other words, if this is a number like 0.1, then there's a 10% chance that the coefficient would be irrelevant, 0. But in this case, you can see all these p-values are very, well, 0 essentially, and that's, I think these asterisks mean standard deviation, so it's better than 4 standard deviations away from 0. So these can all be believed, these coefficients. We'll change the data in a moment, but let's quickly look at the parameters to the linear regression operator. So these are just the defaults. Now you can, by changing this to none, changing eliminate collinear features, use bias of 0, you can change it to a pure a so-called ordinary least squares estimate. You can see the help that's come up there. I tend not to actually, and I don't understand the details of this M5 param stuff, but it seems to work quite well, so I just leave well alone. I'm sure a purist would say I need to understand it, and no, I do, but it's only when you try things and see how the results work in real life do you get the opportunity to re-examine how the model works and make changes to that if you need to. And I've never needed to so far, touch wood. So anyway, let's go back to the data. I'll just run it again. So where are we? We've got a linear regression model. What happens if we change the data? Let's reduce the number of examples. Let's have 100 only. Let's just run it. What do we get now? Now we see that the attribute coefficients have changed. In fact, attribute 1 has disappeared from the reckoning, and attribute 2 itself now is 0.175. It's similar from memory to what it was before, with a larger error. So it's much less confident. It's now 2.6 standard deviations from 0. So there's a 10%, no, I beg your pardon, a 1% chance that this in fact could be irrelevant. So 3 standard deviations here is these, I think, what this means. So you can see this has become less good as a coefficient. In other words, that formula, there's less certainty about it. But the acid test is, let's look at the prediction that this model has made. So this is the test data. So if you remember, there were 100 examples in total, 10 of which are the test data. And we're seeing the result here in the prediction. If we plot prediction as a function of result, well, maybe we can see that there's, I suppose we could argue there's a sort of a trend there. Not very convincing, but I guess it is. And if we now look at the performance vector for that, we can get a sense as to what it thinks the mathematical correctness or how well the prediction is, but based on a mathematical calculation. Now there are a lot of different calculations here. Root mean squared error, I mean, I won't go through these one by one. I'll just look at root mean squared error. That is basically saying you determine the difference between the prediction and the known value, square it, take the average, and then take the square root of that, and that gives you 0.222. Now you can clearly see that that number will depend on the range of the result in general. So if your result ranges from 0 to 100 and you got 0.222, that will be very good. In this case, the range is between 0 and 1, so 0.222 says, oh, that's a 20-odd% variance, is just as a rule of thumb. And a much better one is to use the correlation and squared correlation measures, because these don't depend on the scale. But you can see that the correlation in this case, well, let's use squared correlation. You're supposed to get, the higher this is, the nearer to 1 this is, the better. So clearly, currently we're getting a correlation of 0.16, which is, well, it's not 0, but it's not very good. And you can sort of see that's right, because, well, you know, it's not a very good correlation. So what happens if we increase the number of examples? This time our test data looks like that, and now we are beginning to see, yes, there is a bit of a line happening now. Let's look at the performance vector, correlation. In fact, let's look at the performance to data output. This is the example set version of the performance vector. A bit easy to see it in one go. So the square correlation, it's got better, 0.261. Okay, that's getting better. If I increase it again, actually what will happen is that we will see a very much more convincing line in terms of the plot. And now the correlation and so on, as you can see here, well, it's sort of reached some sort of, it's not getting any bigger, so I think it's convinced itself this is as good as it's going to get. And now what we can do is, if we change the noise, if I reduce the noise by an amount, run it again at that high number of examples, if I now plot the examples as before, there's now much less variation, and now we should see the correlation going up again to the point where if I eliminate the noise completely, which obviously you'd never see in real life, but we'll do it for the sake of argument. Now the chart's a perfect straight line, so essentially the prediction and the result are the same, so it's a perfect model. And now, as you can see, the correlation has gone all the way up to 1. In fact, there's no errors, nothing's gone wrong at all, which is fantastic. This is not real life, so let me just scale that back and put a little bit of error back in. Now what we'll do is let's change how we normalize the data, change the range of some of these attributes. And what we'll do is we'll look at the test data, and we can see that basically the data is in the range sort of 0 to 1 roughly. And let's change, if I just change that to 0, it'll get rid of all of the normalizing I'm doing. So now the actual result is a bigger number. It's no longer between 0 and 1, it's outside that completely. So what does that mean for the various criteria that come from the performance vector? So let's just remember root mean squared error 0.283, and let's also remember squared correlation 0.598. There's a neat trick we can adopt now actually. If I go back here and if I right click and do that, I'll get that example set stored. So if now I rerun the process but with a different parameter, I'll set normalize back to 1. What we'll be able to do is compare the performance vectors before and after. So what I'll do is I'll get rid of the spurious other tabs just to make it a bit easier. So this was the performance vector when I didn't normalize the data, and this is the performance vector when I did normalize the data. And you can see that what I'll do is I'll make it a bit easier to see it all. Let's put it below. So you can see that when I had normalized the data, the root mean squared error is 0.1 as a relation to 1 essentially. When it's not normalized, it's 0.283 in relation to 2 and a bit. So the root mean squared error scales up as the range scales up as well, but the correlation stays the same, as you can see. And there are certain other of the measurements here that also stay the same, and let's highlight them. So it's that one, that one, that one, that one, and that one, and that one there. Yep. So you just have to be a bit careful when you're interpreting the results of a regression problem, because if the data has a certain range to it, then some of the measurements you get out of the performance vector will scale. There is no one right answer here, of course, because your data may legitimately have a range of a certain value, and you're trying to build a model to predict that. By normalizing, you might have to do that under certain circumstances, but there's no hard and fast rule about that. But again, that may affect the performance vector results you get. Okay, so I realise I haven't shown the parameters of the performance regression operator. Here it is, and I've ticked all of the possible criteria. If you don't tick any, you can also override the one it outputs by default. I just leave it like this. Now, in general, there are many other performance operators. The default one, which is performance, you could just use that here, but that doesn't give all of these outputs, and so I tend to use the performance regression one because I'm more interested in not just the ones that the default, which is essentially, I think, root mean squared error is what you get when you use the basic performance operator. Okay, so I'll run the process one more time and just arrange everything in one neat final view. Okay, so this is just the final view. Basically the test data plotted, the performance vector expressed as an example set, and the linear regression model.